So while we're waiting for Jonathan to call in, I can give a little background to what he's going to be talking about. Jonathan, when I first moved to Scranton, Jonathan was one of the very first people that I met there. And he was an undergraduate student in electrical engineering. But he actually came with a very significant background. He had worked as a technician for a number of years and got to the point in his career where in order to advance, he really needed that bachelor's degree. So he came to Scranton, but he was already a very accomplished engineer. And he has a personal passion for VLF natural radio. And so when he saw the personal space weather station project, he's like, I'm really interested in this, but I'm not, he's like, I really want to incorporate VLF into this. And so he said, I'm going to go design my own board that can plug into the personal space weather station. And he's basically done all of this work on his own. And we now, thanks to him, now have a VLF receiver at my QTH in Springbrook, Pennsylvania. And we now have, he's working with Scotty to develop a board that will actually be compatible with the Tangerine. How's it going, Jonathan?
Am I coming through?
Much better. Take it away.
Okay. I apologize for the technical difficulty. Thank you, Nathaniel, for that introduction. This has been a journey, and obviously there is a story. Here are some background resources and previous talks that I did at both TAPR and HamSCI, starting at the TAPR DCC in 2019. What I'm working on is a VLF leaf module for the Tangerine SDR, and I named it the Whistler Catcher. What it is, it's a ULF and VLF data acquisition module for the Tangerine SDR. It utilizes the leaf interface on the data engine. The signal is GPS time-stamped with the SynthDO clock module. It features it features a 4-channel input for up to 4 VLF receivers: E field, north-south B field, and east-west B field, and there's also a spare. The digitized, time-stamped single or multi-channel stream is available via the Ethernet port, and it's compatible with VLF RX tools and Spectrum Lab software. Using VLF RX tools or Spectrum Lab software, it is a feature-rich, scientific, and amateur-grade VLF SDR. It utilizes the TI, Texas Instruments TLV 320 ADC 6140. That's a quad channel, 768 kilohertz, a Burr-Brown ADD converter. It has a 122 dB signal to noise ratio. As I mentioned before, four channel analog inputs only. And we can do up to 768 kilohertz sampling, but for 100 kilohertz VLF operation, the sampling rate you would use is 384 kilohertz. Operation in the Tangerine SDR, the VLF receiver feeds will connect to screw terminals via audio isolation transformers. Electrical isolation is very important for signal integrity. The FPGA will configure the active channels that you choose, their sampling rate, sample length, and it'll configure the master and bit clocks via I2C. The FPGA will also configure the SynthDO DES channel to generate the master clock frequency required for the configuration. So these samples will be time-stamped to GPS time. They're transported via time division multiplexing interface to the FPGA. As I mentioned before, the FPGA will timestamp the samples and generate a VLF RX tools compatible stream via the Ethernet port. The FPGA will also combine all channels, whether it's one or multiple, into a single multi-channel Ethernet, or a single multi-channel stream via UDP socket. There has been some issues with the global chip shortage. The global pandemic has directly affected the global supply chain, and semiconductors and other electronic components are either unavailable and have long lead times. The Intel Max 10 dev board, which was available, that will be used for Verilog development and hardware testing. Scotty WA2DFI is developing an interposer board, like he mentioned in his presentation, called the Data Engine Adapter Board that'll interface to the Max 10 dev board. And there will be a connector that will interface to the TI ADD converter evaluation module, the DC087 DUT board, and that'll plug right into the adapter board. And this will allow for easy dev and testing. This is an image of what the DUT board looks like. It's attached to a, in this picture, it's also attached to the audio interface board that connects to a PC with the TI software. But for this purpose, we're only going to be using the DUT board. And the design is so similar to the Whistler catcher that we could easily use this DUT board for development, which is really nice. This kind of speeds things along and gets right into the Verilog development, which is going to be the most difficult part. This is a drawing of the board, or how the DUT board will attach to the adapter board. You could see it attaches to the end of the board via lugs here. This is a side view. You can see there's some height to this, so there will also be standoffs that this board will rest on, so the connector mates properly. This is a basic schematic. This is not finished. This is the interface connector for the DC087 dev board. And this is what Scotty is currently working on right now. He's working on some interface circuits right now. So what this Whistler catcher leaf module will allow you to set up a VLF receiver at your home, or at some remote site like Nathaniel and I did. Here are some installation photos. This was a tough job. We ran about 270 feet of 2-inch conduit, and we trenched and dug everything out, and we pulled the cable bundle through. This was a fairly intense but very rewarding project. We also ran cables for loop antennas and also for the magnetometer that was mentioned in Scotty's presentation. This is a drawing by Gary Mitkin, AF8A. This is a high-level drawing of the system. So basically, this is the VLF active antenna. That's the PVC pipe that you saw. It has a front end and a line driver stage here. It also has an audio isolation transformer and an isolated DC to DC converter. Right now it connects to a Raspberry Pi and sound card. And on the Raspberry Pi end, there's also an audio isolation transformer and isolated DC to DC converter. The main thing is we want to maintain isolation to keep any mains harmonics from affecting the signal. This is what the inside, what what the board looks like and how it's attached to the antenna. The antenna is made up of copper tape attached to PVC pipe insulation. You can see a board here is constructed with Manhattan construction. Inside, this is what the Raspberry Pi enclosure looks like. This is in Nathaniel's shack. It has a Raspberry Pi and a sound card and some interfacing circuitry, and that connects to his network. And I could log in, I could stream, and I could also capture data as well. Whoops. These are some interesting observations and false detections that I have seen with the system. So the system will automatically detect natural radio emissions, whistlers, and chorus. It automatically detects them with the VLF RX tool software. But there are some false signals that have similar characteristics, such as the first two images that you see here. These are spectrograms of motors starting up in the environment. This could be your washing machine, your refrigerator, your garage door opener. Whenever an AC motor starts up, it gives this interesting characteristic. This on the bottom here is a spheric that modulated the filter too much, and the filter rang for too long, and it created this intermodulation distortion that you see here. This also has similar to what the detector is looking for. The spectrogram here, this is called a tweak spheric. It is a regular lightning spheric that has traveled tens of thousands of miles and has a characteristic frequency dispersion at around 1.7 kilohertz. This also has the dispersion at 3.4. That's the tweak resonant frequency of the Earth ionosphere waveguide. With this system, we were able to detect some really cool stuff. The first is a very weak detection of the VO1NA GPS-locked ULF beacon at 8.72 hertz. This is a GPS-locked carrier that is used for transmitting carriers, that is used for transmitting digital mode messages using the EbNaut mode at frequencies below 9 kilohertz. This is a very exciting frontier that amateurs are just starting to get into. The one below it, this is a power spectrum of the Christmas Eve SAQ transmission. This peak in the middle here, that is the actual power spectrum of the transmission that was received at the antenna site. On the right here, you have an NAA diurnal with you can see around 1730 UT in this plot. There is a sudden ionospheric disturbance that was detected. So these are very exciting signals. And I talk about those signals more in my poster. I invite you to look at my poster. There's much more background and detailed information that will satisfy your curiosity. I talk about the SIDS, the SAQ transmission, the installation, and a possible sudden enhancement of atmospherics event caused by the Tonga ash cloud. One thing that I'm also excited about that this system will support is the new EbNaut digital mode, and I am currently working on a rig very similar to what you see here that will allow you to transmit messages of a few characters below 9 kilohertz. And these messages have been received from Europe to the US. And this uses the new EbNaut digital mode. This is on the left here is the EbSynth program used to generate the GPS locked carrier and also modulate the message. On the right here is an example rig. Very simple, uses a Raspberry Pi, a Raspberry Pi sound card, and a GPS. That's all you need to get started. You obviously need a power amplifier to transmit your signal, but it is very easy to get started. It's highly technical, so if you enjoy that sort of thing like I do, then it's a great. This is a really great project. I'm going to build a really nice rig in a nice enclosure for easy transmission using an audio power amplifier. So that's going to be a really cool project, and that presentation is coming to the TAPR DCC coming in September. I also have some resources and links. I will provide a copy of my presentation on the Google Drive so everybody could have this. Different sorts of resources and information that will allow you to kind of get started into this hobby if you haven't, and I invite you to do so because it's very exciting. And with that, I would like to thank everybody that has offered me help and support, including Paul Nicholson, the VLF community, Nathaniel for his support and motivation for this project and allowing me to host this system at his QTH. Gary Miller for his updates to GPSD, which is used in this system, and Scotty Cowling, WA2GFI, for his engineering support with the Whistler Catcher module. With that, I'm going to end the presentation. Thank you.